So if we want to find the derivative of 2z plus 5 to the third times 3z minus 1 to the fourth, what rule do we need to use?
Product rule?
Product rule, exactly. This is one function, u, times some other function, v, right? We've got u is 2z plus 5 cubed, so I'm going to write that here. And v is 3z minus 1 to the fourth. All right, so as we do the product rule, y prime should be u. So we got that, 2z plus 5 to the third times the derivative of v, right? So how do I find the derivative of v? Well, v is equal to 3z minus 1 to the fourth. That's a composition of two functions, right? So I should rewrite that as v is equal to something to the fourth. How about, since we've already used u and v here, how about we'd say just a to the fourth with a equal to 3z minus 1. Does that sound okay?
Yes.
Okay. So what's the derivative of v?
4a cubed.
4a cubed. And what's the derivative of a with respect to z?
3.
3. So this becomes 12 times a cubed. And a is 3z minus 1, so 3z minus 1 cubed. Everybody good with that so far? So u, and then derivative of v, and then plus v, 3z minus 1 to the fourth, derivative of u. And for the derivative of u, we've got u is equal to, I don't know, something to the third. So how about b to the third? With b equal to 2z plus 5. And what will du db be? That should be 3b squared. And db dz, the derivative of b with respect to z, ought to just be 2. So what do we get? We get a 6, and we get a b, which is 2z plus 5 squared. Everybody agree with that? Cool. This answer right here is perfectly good. There's no issue with that answer. But what if I ask you, when does our derivative equal 0? Well, having this plus sign in the middle there complicates figuring out when this equals 0. So what we want to do is we want to be able to factor it out, look for common terms. So first, let's look at the constants. What's the constant in our first term here?
12.
And our constant in the second term is?
6.
6. So what do they have in common?
6.
Right. So we'll take out a 6. Then what else do they have in common? Do they both have a 2z plus 5 to a power?
They do.
They do. They both have a 2z plus 5 to what power?
Squared.
Squared.
Squared, right? We're going to have something left from the first one, but they both have at least a squared. And then what about the 3z minus 1?
Cubed.
Yeah, they both have a cubed. And that leaves me with, well, from the first one, I took a 6 out of the 12. That's going to leave me with a 2, right? I took a 2z plus 5 squared out of the 2z plus 5 cubed. That ought to just leave me with 2z plus 5 to the first, or just a 2z plus 5. And then I took a 3z minus 1 cubed out of a 3z minus 1 cubed, so that part's good. So that's everything from the first piece. What about the second piece? Took a 6 out. I had a 6, so that's good. I took a 2z plus 5 squared out of a 2z plus 5 squared, so that's good. All that's left is I took a 3z minus 1 cubed out of a 3z minus 1 to the fourth, so that ought to just be 3z minus 1. And so we end up with 6 times 2z plus 5 squared times 3z minus 1 cubed times what? 2 times the 2z is 4z plus the other 3z is 7z. And then we got a 10, and minus a 1 is a 9. So this answer is a better answer. Would I accept this answer up here? Sure. But you better be able to get to this one in case I ever ask you when this derivative equals 0. Good or no?
Good.
Good. All right. Any questions on that one? All right. Let's take a look at this one. 3x plus 1 to the 6th power times the square root of 2x minus 5. You guys think you could find the derivative of that using the product rule and the chain rule?
Yes.
All right, I'm going to give you like 2 minutes to give that a try, and then we'll work on simplifying it together if we need help with that. So you got like 2 minutes. Ready, go. What did f prime of x equal? Should have been the first piece, 3x plus 1 to the 6 times the derivative of this. And what was the derivative of root 2x minus 5? That's root u with a u equal to 2x minus 5, right? So root u ought to be 1 over 2 root u times the derivative of u. Is that what you got for the first piece of it with the product rule? Hopefully.
Yeah.
Yeah.
And then plus, and then we just had a root 2x minus 5, right? And then a 3x plus 1 to the 6th, well, that's u to the 6th with u equal to 3x plus 1. So that ought to be 6 u to the 5th times the derivative of u. Any questions, issues, problems, concerns about that?
So why would we start with the product rule instead of the chain rule?
We're going to have to use the chain rule within the product rule, right? The reason we start with the product rule is because at its core, at its base, this is one function times another function. And so as long as it's one function times another function, no matter what, unless you have a way to combine them together so that it's not that, you're going to have to use the product rule. And then within it, you can use the chain rule. But there's no way to write, this function as y equals something simple like, u to the 6th or u to the, or the square root of u, right? Because there's too much going on in here to write it as a single composition of functions. Does that make sense?
Yeah.
Cool. All right, so first off, these 2's will cancel. Everybody agree with that? And then what can we do? To get this to simplify down, we're going to need a common denominator. So how about we multiply by root 2x minus 5 and root 2x minus 5? Yeah? Great. So now we can combine these together into one fraction. 3x plus 1 to the 6th plus, we're going to have an 18. We're going to have a 3x plus 1 to the 5th. And we're going to have root 2x minus 5 times root 2x minus 5, which is just 2x minus 5. All over root 2x minus 5. Good or no so far?
Good.
Good.
All right. And then from there, if we want to get the numerator to all just be multiplication, we're going to have to factor out common terms. So what's the common term to factor out?
3x plus 1 to the 5th.
Exactly. And that'll leave us here with just a 3x plus 1. And on the other side, it'll leave us with an 18 times 2x minus 5. And as we combine this together, we've still got the 3x plus 1 to the 5th. But now we've got what? We've got 36x plus 3x is 39x. And 18 times negative 5 is negative 90. Plus 1 ought to be negative 89. Good or no? Any questions, any issues with that? Any problems? Great. All right, let's look at another one. Tangent cubed of 4x. So what are we going to do with tangent cubed of 4x? Any ideas on that? Is this two functions being multiplied together, or two functions divided, or is it a composition of functions? What is this?
It looks like a composition of functions.
It does, right? So when we think about a composition of functions, what is the outermost function that we've got? What's the like?
The tangent cubed.
Yeah, the tangent cubed, right? We're cubing that tangent of 4x, right? This means, doesn't this mean tangent of 4x cubed? That's the same thing, right? So the outermost function part of this is, we'll say y equals u cubed with u equal to tangent of 4x. So we should be able to set up a chain rule that the derivative f prime of x ought to be the derivative of y, which is 3u squared, times the derivative of u. Well, how do we find the derivative of the tangent of 4x? Isn't that in itself a composition of two functions? Isn't that u equals tangent of, we'll say, v, with v equal to 4x, with a composition within the composition?
Yes.
Yeah, all right. So how do we take this derivative? We need the derivative of tangent v, which is secant squared v. And then we need to multiply that by the derivative of 4x, which is 4. So we end up with 12 u squared. So that'd be tangent squared 4x. And then secant squared v, or secant squared 4x. Good or no? You guys are awfully quiet there today. Are we doing okay or no?
I think so. Wait, can I have like a few more seconds?
Yeah, can you leave it off?
Sure.
Thanks.
Can you explain how you went from 3u squared secant squared v times 4 back down to the final one?
Yeah, so we got the 3 and the 4, that's 12, right? We multiply the 3 times the 4.
Yeah.
All right, so then we have u squared. Well, u was tangent 4x, so that's just tangent squared of 4x, that's this. And then we have secant squared v, and v was 4x, so we just replace that with the 4x, secant squared 4.
Okay, thank you.
Yeah, no problem. Should we do another one of these with it? Let's do another one of these where it's like a composition within a composition. I wasn't going to, but it sounds like you guys are having a little trouble, so let's do that. Let's do y is equal to the square root of sine of x squared. And we want to find what is y prime. What's the derivative of y? So hopefully we see that this is a composition, that this is the square root of u, right? With u equal to
Sine x squared.
sine of x squared. So what's the derivative of the square root of u? That ought to be 1 over
2 root u.
2 root u times the derivative of u. But since u is sine of x squared, we're going to have to use a composition. So u is the sine of, we'll say, v, with v equal to x squared. And so what's the derivative of sine of v? That ought to be
Cosine v.
cosine v. And what's the derivative of x squared? That ought to be
2x.
2x. So we will see, hopefully, that the 2's will cancel each other. But we end up with cosine of v, which is cosine of x squared in the numerator and an x in the numerator. So we got x cosine x squared all over the square root of u, which is the square root of sine of x squared. Does that make sense? Does that help? To do another one
Yeah.
like that? Yeah.
Yeah.
Feeling okay about it now?
Yeah.
Yeah.
All right. These chain rule within the chain rule problems, they definitely pop up often enough on the AP test. So there'll be some of these on, you'll have a homework assignment where you have a bunch of these chain rule within the chain rule problems. So. Not tonight, because I need to teach you lots of other derivatives first. But. All right. Let's see if we can find the slope of the line tangent to y equals sine to the 5th x at the point where x is pi over 3. So what's our first step going to be here? Anybody? First step? If we want a slope of a tangent line, what is that asking us to find?
The derivative.
It's asking us to find a derivative, exactly. So we need to find y prime. This is sine to the 5th, so that's y equals u to the 5th, with u equal to what?
Sine
X.
U equal to sine x. So what's the derivative of u to the 5th?
5u to the 4.
That should be 5u to the 4th. And then times the derivative of sine x, which ought to be
Cosine x.
cosine x. And u was sine, so this is y prime equals 5 sine to the 4th x cosine x. Everybody good with that being the derivative?
Yeah.
Cool. All right. So next up, what?
Plug in the x value.
Plug in our x value. So at x equals pi over 3, what do we get? We get 5 times the sine of pi over 3. What's the sine of pi over 3?
Root 3 over 2.
Root 3 over 2 to the 4th. And then the cosine of pi over 3, which is a half, right? Then what? Multiply it all out. Root 3 to the 4th ought to be just 9 times 5 is 45 times 1 is 45. And then 2 to the 4th times 2, or 2 to the 5th, is 32. Good or no? Any issues with that or no?
Like real quick, like why did you multiply the like in the derivative the 5u to the fourth by cosine x? Like I understand why you got 5u in the fourth, but where'd you get that cosine x from?
So, right, this is our 5u to the fourth, that derivative, and then the derivative of this is our cosine x. So there's your 5u to the fourth, and then there's your cosine x. That's the chain rule piece, right? It's u to the fifth with u equal to sine x. You got to multiply the derivative of this by the derivative of this.
Okay, thank you.
Does that make sense? Yep.
Yeah.
Okay, cool. All right, let's do another one. Let's find all of the horizontal tangent lines for cosine 2x plus 2 cosine x on the interval from 0 to 2 pi. So how are we going to do that?
You need to take the derivative and find when it's equal to 0.
All right, horizontal tangent lines means derivative y prime equals 0. So derivative equals 0 means find the derivative. And let's see, for cosine of 2x, that's the cosine of u, right? With u equal to 2x. So that should become negative sine u times 2, or negative 2 sine 2x. Everybody okay with that derivative? That's chain rule, right?
Yep, all good.
Okay. And then what about 2 cosine x? That one should just be minus 2 sine x. And we want to know, when does this thing equal 0? So, how do we solve that equation? Any thoughts?
We could factor out the -2.
That's a good start. Negative 2 times sine 2x plus sine x equals 0. And now that we've factored out that negative 2, can't we just divide by it?
Yes.
Right, we can just get rid of that negative 2, right? Because 0 divided by negative 2 is just 0. And how do we solve the rest of this? How do we solve sine 2x plus sine x equals 0? What can I do with sine 2x? Besides make it look like bacon underneath it.
Could you use a chain rule to separate it? No, that doesn't work.
Nah, because we're not taking another derivative.
Right, yeah.
A double angle.
Double angle identity, yeah. Sine 2x is equal to 2 sine x cosine x. And we have a plus sine x equals 0. And now what can we do to solve this?
Divide by sine x.
So we can't divide by the sine x because that eliminates some of the possible answer choices, but we can factor out the sine x, which is exactly what we want to do. And now, if sine x was equal to 0, that would give us some solutions. And if 2 cosine x plus 1 was equal to 0, that would give us some other solutions. So when does sine equal 0? At x equals
0 and pi.
0 and pi, good. And what about when does cosine x equal negative a half?
At 4 pi over 3 and 11 pi over 3.
4 pi over 3 is one of them,
Oh, whoops.
but not
Um,
11 pi over 3. So 4 pi over 3 is in the third quadrant. We also need an angle in the second quadrant. These are values that you should all know.
2 pi over 3.
2 pi over 3. So we have 4 places where this function has horizontal tangent lines on the interval from 0 to 2 pi. Let's take a look. In Desmos, what was it? Cosine 2x, right? Plus 2 cosine.
Yeah.
So if we look, looks like there should be one, right? A horizontal tangent line here at x equals 0, where that local maximum there is. There should be another one down here at 2 pi over 3, another one at pi, another one at 4 pi over 3, and then no more until 2 pi. And 2 pi was not on our actual interval, right? Because we had an open interval on that side, non-inclusive on the 2 pi. Good or no?
Yeah, that's good.
All right. Last thing we're going to do with this basic chain rule stuff today, and then we're going to move in to another technique for technique for derivatives, is we want to find a reason why the slope for every line tangent to 1 over 1 minus 2x to the third power is positive. So if we're talking about slopes of the tangent lines, we want to show in this case that the derivative is always positive. We want to show that the derivative is always greater than 0. So in order to do that, we're going to probably need a derivative. Yeah.
Yep.
So how are we going to take that derivative?
We could use the reciprocal.
Okay, we could use the reciprocal rule. All right, so this is a function to the third power, though, so we have to use the reciprocal rule in conjunction with
The chain rule.
the chain rule, right? So this is 1 over u cubed with u equal to 1 minus 2x. Yeah? So how do we take the derivative of 1 over u cubed? That ought to be negative, right? G prime, the denominator, its derivative. What's the derivative of u cubed?
3u squared.
3u squared.
Okay. Over the denominator squared, u cubed squared is u to the 6th. And then we need to multiply that by the derivative of 1 minus 2x, which is negative 2. So we should be able to simplify a little bit. The negative should cancel, right? The 3 times the 2 should be a 6. So we have 6u squared over u to the 6th, or 6 over u to the 4th, if we simplify the u squared over u to the 6th, right? Good or no?
Good.
And if we replace the u with what it is, 1 minus 2x, we have 6 over 1 minus 2x to the 4th power. And we want to know, why is this always positive? Well, it's something divided by something else. In order for that to be positive, both of these would have to either be positive or they both have to be negative. And 6 is always positive, right? What about 1 minus 2x to the 4th power?
It's also always positive.
Yeah, it should be positive because we're raising it to the 4th power. So we'll say positive unless x equals what? A half, right? If x is a half, then this would be 0, and then it would be undefined. which would not be positive, true? But luckily, in our original function, x cannot equal 1/2, right? Because that makes our original function undefined. Therefore, there's no tangent line at x equals 1/2. So we don't need to worry about that. So we'll say this is always positive. And if we were to look at this, does that make sense or no? Before we start looking at the graph.
Yeah, that makes sense.
Cool. So here's the graph, 1 over 1 minus 2x to the third. Clearly, it's got that asymptote at x equals 1/2. So we're good there with that value of 1/2. And if we look at the slopes, well, yeah, it sure is not increasing very rapidly, but you can tell, especially if we zoomed in a little bit, you'd see, yeah, that's increasing very slowly, but it's increasing. And then it starts to increase very rapidly, right? And these slopes are all positive on this piece of it. And then again over here, right? These are all positive slopes. Anywhere I drew a tangent line, slope would be positive, even though over here, it's not increasing by very much. It's still increasing very, very slowly. And the tangent line would always be having a positive slope. Good or no?
Good.
Great. All right. We're going to move forward into something new now. That is actually a little bit of an application of the chain rule. And that's called implicit differentiation. So implicit differentiation is just another way to take a derivative. But we use it when we have an equation that cannot be written as a single function of x, right? So here I have x cubed plus y cubed minus 9xy equals 0. Clearly, if this is the graph of this is clearly not a function, right? There's your vertical line test. Fails the vertical line test miserably, right?
Yep.
Yep, doesn't pass that vertical line test, right? This is not a function. Anybody see a nice, easy way to solve that for y? Like we could subtract the x cubed and factor out a y, but that's still going to give us a bunch of y terms in there that are going to be a little bit annoying. No good way to solve this for y to then just take a derivative. So we have to use this technique of implicit differentiation anytime we have what we call an implicitly defined equation or an implicitly defined relation, where we've got x's and y's in here, and we can't explicitly solve just for y and get only one function. So the method that we're going to use first requires us to take the derivative of both sides with respect to x. And if I do that, we're not going to do it with this equation right now, but if I do the derivative of all of that with respect to x, there's some issues in there, right? The x cubed is easy, isn't it? What's the derivative of x cubed with respect to x?
3x
3x squared.
squared.
3x squared. But taking the derivative of y cubed, something in terms of y with respect to x, is a much bigger issue. We can't do that. We have to treat that as if it is a composition of two functions. Okay? Where if we're saying this is some function u equals y cubed, right? And then we take the derivative of it with respect to its own variable, y, and then we multiply that by the derivative of y with respect to x. So what's going to effectively happen is anytime I take a derivative, so if you take a derivative of a y term with respect to x, you always have to attach a term that is dy dx to it. So you'll take the derivative of this with respect to y. What's the derivative of y cubed if I say differentiate that with respect to y?
3y squared.
3y squared. And then we're going to multiply it by dy dx. by the derivative of y with respect to x. And that's effectively the chain rule. We're treating it as if it's a composition of functions where we're going to take the derivative with respect to y and then the derivative with respect to x and multiply them together. Okay. So we're going to start this off with a real easy one that doesn't have something messy like a minus 9xy in it. Oh, sorry, I didn't finish talking about this. Once we've gotten that derivative, then we just need to solve for the dy dx, and we'll see how to do that. It becomes increasingly more difficult depending on the annoyingness of the equation that I give you, but the first couple won't be too bad. So we want to find the derivative of y squared equals x. We want to find dy dx. So effectively, we want to find the slope of the tangent line to this equation. Anybody know what that equation looks like? What does y squared equals x look like?
Square root of x.
It looks like the square root of x, but it also looks like the negative square root of x, both at the same time. It's a parabola on its side. Right? If we were to solve that for y, we'd have to get y equals square root x, that'd be the top half, and we'd have to get y equals negative square root x, that'd be the bottom half, right? So we would need two different functions to get our single equation y squared equals x. Okay. So if we need to find dy dx, we're going to take the derivative with respect to x of both sides. And on the right-hand side, it should be very easy. What's the derivative with respect to x of x?
1.
1. But on the left-hand side, we have to take the derivative of a y term with respect to x. So we'll take the derivative with respect to y of y squared, and then we will multiply that by dy dx. And from now on, I'm not going to write all of this out each time. We're just going to do it. So what's the derivative with respect to y of y squared?
Two y.
2y.
It'd be 2y, and then we just attach this dy dx to the end of it. So we have 2y dy dx, giving us dy dx equals 1 over 2y, which we should note is very different than any other derivative we've taken so far this year. Right? All the other derivatives we've taken so far, when we took a derivative with respect to x, we ended up with something that was all in terms of x. But in this case, we've just ended up with something in terms of y. And that's okay. The good news is that will help us account for both the upper and the lower pieces of this parabola. So let's choose a couple of points that are on this parabola. For example, the point 4, 2, and let's do the point 4, -2. Those would both be on there. Everybody agree with that?
Yes.
Yeah. So if I were to evaluate this for the point 4, 2, what would the slope be?
One over 4.
Right. And what if I did this one?
1 over -4.
Right. It'd be negative a fourth, right? So the equations for the tangent lines of each of these would be y minus 2 equals a fourth times x minus 4, and y minus -2, or y plus 2, equals negative a fourth times x minus 4. And even though we have the same x value, because they give us different y values, it gives us a different slope. And we should be able to go in here and say y minus 4 equals 1/4 of x minus 2. No, is that what it was? X minus what?
The point was 4, 2.
Oh, I did it backwards, didn't I? Ha. Y minus 2 equals 1/4 times x minus 4. There we go. is what happens when I go away from the screen I was on for Desmos. Right, there's the point 4,2, and very nicely tangent line there at 4,2. And the other way we did it, it was y plus 2 equals negative 1,4 times x minus 4. And that's our tangent line on the other side at 4, negative 2. And so it takes into account both sides of this. And that's why it's important to have that y in the derivative there. Any questions or issues with that? All right, let's do another one. We want to find dy dx if y squared equals x minus 1 over x plus 1. So once again, this should be pretty straightforward. We're going to take the derivative with respect to x of both sides. I suppose we could look at what this looks like. You guys want to see what this looks like? What do we have? X minus 1 over x plus 1. And we got something like this. Clearly not a function, right? Definitely not. And we want to find the derivative. So what's the derivative with respect to x of y squared? First, we take the derivative of it with respect to its own variable, with respect to y, 2y, and then we attach a dy dx to it. Good or no?
Good.
By attached, do you just mean like multiply?
Yep, it's just multiplied by it, yep.
Okay, thanks.
And then this derivative with respect to x of x minus 1 over x plus 1, that's a, what is that? That's a quotient rule problem, right?
Yes.
Okay. So we end up with denominator, derivative numerator, minus numerator, derivative of the denominator over the denominator squared. And if we simplify that out, what's this numerator going to become? X plus 1 minus the quantity x minus 1. So the x minus the x will cancel. And then we have a 1 minus a negative 1, which ought to be 2. So we got 2 over x plus 1 squared. And if we want to solve for dy dx, we need to divide by that 2y. And we end up with a derivative that is 1 over y times x plus 1 squared. Good or no?
Good.
Great. What if we wanted to find a tangent line at some point?
Then we would plug in the point.
Just plug in that point. We see a nice point that looks convenient over here. I don't know. I don't see any real nice looking points. Do you guys? And the only one is 1, 0, right? Well, let's look at 1, 0. That'll be an interesting one. If we were looking at x equals 1, y equals 0, what does that give you? It gives us 1 over 0 times 1 plus 1 squared, or 1 over 0, which is undefined, right? Which tells us that at this point, 1, 0, our tangent line should be vertical. And it sure looks like it would be, doesn't it?
Yes.
Yeah. Great. All right, let's do a slightly more difficult one. You guys want to try and do this one real quick on your own? Shouldn't be too bad.
Yes.
All right, I'll give you like a minute and a half here. Ready, go. And we'll take the derivative with respect to x of x. And we'll take the derivative with respect to x of tangent y. So the derivative with respect to x of x is just
1.
1. And the derivative with respect to x of tangent y, well, what's the derivative with respect to y of that? It should be
Secant squared y.
secant squared y, and we'll multiply that by dy dx, since we took the derivative of a term with y in it. So we end up with 1 over secant squared y equals dy dx, or we could say that's just cosine squared y. Good or no?
Good.
Great. All right. Let's do another one that is a little bit more difficult now here. So we've got x squared y plus xy squared equals 6. We take the derivative with respect to x of both sides, right? And the right-hand side of that ought to be really easy. What should the right-hand side of that be? Should just be a 0. But then the left-hand side, what can you tell me about x squared y? How do I take its derivative?
Do you need to use the product rule?
You definitely do. This is a function times another function. It's x squared times y, a function times a function. So we'll do x squared first, right? First function times the derivative of the second. So what's the derivative of y with respect to x?
It's 1 times, it's 1 times d dx.
dy dx, but yeah. Yep, 1 times dy dx. And what about the second part of this? We need to do the y times the derivative of x squared. What's the derivative of x squared?
2x.
Do I need to attach a dy dx to this at all?
No.
No.
No, I don't need to this time because I didn't actually take the derivative of the y part on the second part of the product rule. Okay. Everybody good with that?
Yeah.
All right. What about the xy squared?
Use product rule again.
We're going to use the product rule again. Exactly. So the first part will be x, right? Times the derivative of y squared, which is what?
Two y times dy over dx.
2y dy dx, exactly. And then the last part is the derivative of x, which is just 1, right? Times y squared, which since we weren't taking the derivative of it is just y squared. Everyone good there or no?
Good.
All right. So now we need to solve for dy dx. Now it's going to get slightly more complicated than it had with the other ones. First off, let's clear out anything that doesn't have a dy dx in it to the other side. So that'll be this 2xy becomes a negative 2xy, and this y squared ought to become a minus y squared. Good or no? So far?
Good.
Good.
And on this side, all that's left are these two terms. What do they have in common?
X and dy over dx.
Right, they have an x and they have a dy dx. So we're going to want to factor out at least the dy dx. There's not really much of a reason to factor out the x. If you want to, you can, but we're just going to factor out the dy dx, which gives us x squared plus 2xy. And now we can just divide both sides by x squared plus 2xy and get our derivative. And if you'd factored the x out on this side also, you just have x times x plus 2y down there. But that's not necessary. Any questions or issues with that? Everybody okay with that? All right, let's see if you guys can do this one on your own. I'll give you 2 or 3 minutes here. See if you can find the slope of the circle, or basically the slope of the line tangent to the circle at the point 3, -4. Ready, go. The derivative on the left-hand side with respect to x should give us what?
Two x plus 2y times dy dx.
Perfect. And on the right-hand side, we should get
0.
0.
The derivative of a constant should be 0. So we'll subtract the 2x, 2y dy dx equals -2x. And we'll divide by the 2y. So dy dx equals -2x over 2y, or simplify it to -x over y. And then we want to know the slope at the point 3, -4. So we'll just plug in 3 for x and -4 for y to get 3/4. And if we wanted to, we could go in and say, this is the line, y plus 4 equals 3/4 times x minus 3. This is what it asked for, was the slope. But it'd be nice to know what the actual equation was. And we could graph it and show what did we have? Now I forgot already. Y plus 4, right? All right. 3/4 times x minus 3. And there it is. Tangent to our circle at 3, -4. With a slope of 3/4. Everybody good with that or no?
Yeah.
Cool. All right. Let's show that the slope of this equation, 2y equals x squared plus sine y, is defined for every point on its graph. So no vertical tangent lines on this one, basically is what we're saying. How will we do that? First, if we're going to show that the slope is defined, that slope is a derivative, right? So what's the derivative with respect to x of 2y?
Two times dy dx.
Good. 2 times dy dx. What's the derivative of the x squared?
2x.
And the derivative of the sine y?
Cosine y times dy over dx.
Perfect. And now we have 2 different dy dx terms on opposite sides of the equal sign. So we'll bring one to the other. And we'll factor out the dy dx. And if I factor out the dy dx, I'm just going to divide by that 2 minus cos y. And the question was asking us to show that this slope is defined for every point. So first off, is 2x always defined?
Yeah.
What about cosine of y? Can I take the cosine of anything?
Yeah.
The only thing that would make this undefined is if the denominator, 2 minus cosine y, equaled 0, right? Find places where that's true. That'd be when does cosine y equal 2? When does cosine of y equal 2? Does it ever equal 2?
No.
No, because we know that the cosine function is always between -1 and 1. So that will never happen. And just for fun, we could look at the graph of this and see that there's no vertical tangent lines to it. We had what, 2y equals x squared plus sine y. And we get this, I'll zoom it out a little so you can see. You get this sort of like wavy little parabola kind of looking thing, true? It's like a parabola if it's done too much drugs or something. Everybody good with that?
Yeah.
All right, cool. All right, we got one more problem, then we'll be done for the day. Let's see if we can find the equation of the line tangent to this figure 8 curve at 2 root 5 over 3, comma 2. So we'll work through this one together since we're kind of running out of time here. First off, to find the equation of the tangent line, we need the slope of the tangent line, which means we need the derivative. We need dy dx. So what's the derivative of y to the 4th with respect to x?
Four y to the third times dy dx.
4y to the 3rd dy dx equals, what about the 9y squared? That ought to become 18y. 18y dy dx, right? And what about the minus 9x squared? That ought to become minus 18x, just minus 18x, right?
Right.
All right. And just in the interest of getting positive values here, let's put the 18x over there and subtract the 4y cubed. We can factor out the dy dx. And when we do and we divide, we end up with this as our derivative, which could be simplified, right, to 9x over 9y minus 2y cubed, if we wanted to. Everybody okay with that or no?
Yeah.
Cool. And where do we want to evaluate this? At the point 2 root 5 over 3, comma 2. So if we do that, our numerator is going to become 18 root 5 over 3. And our denominator is going to become what? 18 minus 16. So we've got 18 over 3, which is
6 root 5.
6 root 5 over 2, which is 3 root 5. So what should our tangent line's equation be? It ought to be y minus 2 equals 3 root 5 times x minus 2 root 5 over 3. Any questions or issues with that?
No.
Great, let's graph it and make sure that we did it right. Y to the 4th equals, what do we have? We had 9y squared, is that right? Minus 9x squared.
Yeah.
There it is. And our tangent line was y minus 2, I believe. Should be 3 square root 5 times x minus, what was it? Was it 2 root 5 over 3?
Yes.
Great. There it is. And right there at that point, which is the point 2 root 5 over 3, comma 2, we are tangent to our figure 8 curve. We might hit it again later a couple times with that same line, but at that specific point, we are tangent to the curve. Everybody good there?
Yep.
Wonderful. Any questions on that or anything else that we did today?